Hey guys, it's Mrs. Rooker again. Go ahead and do example number 1 really quick and then unpause your video and I'll have the answer. Okay, here's a rough sketch of what the graph's going to look like. It's decay, it's got an asymptote up at 1, so your answer is going to be D. Alright, number 1. L of I is the loudness of a sound in decibels, where I is the intensity of a sound. So I guess I should be highlighting some stuff. I is the intensity of a sound in watts per square meter, and I of sub 0 is the intensity of a barely audible sound, which is about 10 to the negative 12. So that's a constant. It's going to be 10 to the negative 12. The function below will calculate the loudness of a sound given its intensity. So it's kind of a weird formula, but we're just plugging and chugging. So this one should be pretty easy. So we're supposed to be finding the loudness of a sound. So this part represents the loudness of the sound. So I don't know that yet. I'll just put L sub I. That should be an I, not a 1. Right, equals 10. My 10 looks like a log. 10 log of I over I sub 0. So we're trying to find the loudness of a sound if the intensity is 10 to the negative 2. So we'll put that for the intensity for I over I sub 0 was a constant, and it was 10 to the negative 12. And now all I have to do is type that into my calculator and then get an answer. So you want to be careful when you type it into the calculator. So we're going to do 10 log, and then I'm going to do a fraction. I just learned this recently. How to do this, we go alpha, and then this y equals button, and our first option is going to be the fraction. So that's really nice. 10 to the power of negative 2 over 10 to the power of negative 12. And then, I don't know that it's fully necessary in this problem, but just in case, I'm going to close my parentheses. And I get 100. So L of, I guess I could have put 10 to the negative 2, is going to be 100. So when the intensity is 10 to the negative 2, our answer is 100. All you really need to put is 100. Okay, moving on. An important application of exponential equations is Newton's law of cooling. This law states that for a cooling substance with an initial temperature, T sub 0, the temperature T, so big T, after little t minutes can be modeled by that function, where T sub R is the surrounding temperature and R is the substance's cooling rate. So if CSI Brody finds a body that is currently 86 degrees Fahrenheit in a hotel room that is 73 degrees Fahrenheit, and the cooling rate of a human corpse is 0.0033, how long ago did John Doe die? So, plugging and chugging again. So we're trying to find out how long it's been since John Doe died. Well, the time was little t, so we're trying to solve for little t. So we need to plug in for all the other things. So that means we need to find out what big T is first. So big T, what did big T stand for? It stands for the current temperature of the body. So that was going to be 86. 86 is the current temperature of the body. T sub 0 would be the initial temperature of the body. So they didn't write it in here. But I believe the initial temperature of a body we're going to assume is 98.6 is kind of the standard. I believe that's the standard body temperature. We're just going to go with that. Minus T sub R. So T sub R is the surrounding room temperature. So that was 73 degrees. Times e to the negative RT. So the rate is, they gave us here 0.0033. T we don't know yet. Plus T sub r again is 73. All right, so from here, we will now start to solve. So we need to isolate r first. R. We're gonna have to isolate all of this first, then we can log both sides. So I want to get rid of the 73 first. I'm going to subtract 73 from both sides. So 86 minus 73 is 13. And then I'm also going to simplify what's inside these parentheses. When I subtract 98.6 minus 73, I get 25.6 times e to the negative 0.0033. So e is still not quite isolated. I need to get rid of that 25.6. So I'm going to divide both sides by 25.6. So I'll have 13 divided by 25.6, which I could get a decimal, but I'm more precise if I avoid that. Negative 0.0033. Now that e is isolated, I natural log both sides. It's always natural log that you're going to use when you have e, because natural log and e have the same base, so they'll cancel each other out. So that all cancels. And then my final step, oops, I forgot my t. What times? There should be t there, t there. Now to solve for t, I need to get rid of the negative 0.0033. So I divide by negative 0.0033. Type all of that into my calculator, and that'll be my answer for t. Oops, there. Natural log of 13 divided by 25.6, close parentheses, divided by negative 0.0033 equals 205.34. And then we want to look at what our units are. Right here, it said t minutes. So 205-ish minutes. All right, moving on. Exponential growth for population, blah, blah, blah. Where A is the final population, A sub 0 is the initial population. So that's really like our P, our principal value in the formula that we're used to. So the exponential models below describe the population for an indicated country. A is in millions and T is in years after 2016. So this is all starting in 2016. So all of the principal values are the populations as of 2016. So for India, the principal value was 1095.4 million. So that's the population in 2016. For Iraq in 2009, that's going to be 3 years later. So we're going to have to plug in 3 for T. So for Iraq, it's 26.8 e to the 0.027 times 3 years later. So this one, I don't need logs to find. I just plug this into my calculator. 26.8 times e to the 0.027 times 3 power. And I got 29.06 million. So it went up, but not a ton, because it wasn't a crazy high rate, and, well, I mean, it's kind of high rate for population increase, but wasn't that many years. All right, and then when will India's population be 1392 million? So this one will involve logs to solve, because we need to solve for t, which is up in the exponent. So 1392 is what we put in front, because that's what we want the population to be. And then we plug into the formula for India, so that's going to be 1095.4 times e to the 0.014 t. Like always, we need to isolate e before we do anything, so I'm going to divide away the 1.0, or not 1.0, 1095.4. So I'm just going to erase that because I divided it away. Now I natural log both sides so that I can cancel out the e. So that canceled out the e. And last but not least, to solve for t, I divide both sides by 0.014. Type all of that into the calculator. Oops, that's not my calculator. Natural log of 1,392 divided by 1095.4, and then close parentheses and divide that by 0.014. All right, 17.1-ish years. So if we want to actually put a year, so after 2006 plus 17 years is going to be about the year 2023, which is coming up pretty soon. All right, couple more. The formula T equals natural log of 4 over R gives you the time for a population with a growth rate R to quadruple. New Zealand's population in 2006 was 4.1 million. The population increases at a rate of 1% each year. How long will it take for New Zealand to quadruple their population? So we're just plugging and chugging into this formula. So since it asks how long it takes, we're solving for t. So we don't know what t is. And then we just plug into the formula. We know that the rate, the population rate increases at 1% per year. So we're going to put 0.01 down there. And just type into the calculator. It's really nice when they give us that formula. So natural log of 4 divided by 0.01. Make sure to close your parentheses after natural log of 4, unless you click enter in between. All right, so it will take 138-ish years, 138.6 years to quadruple, which hopefully kind of makes sense because it's a pretty low increase rate or pretty low percentage, so it's going to take a long time. How long will it take New Zealand to triple its population? Well, a couple ways we can go about doing this, but because we're a little low on time, I'll just give a little insight here. The reason that this was the quadruple formula is because we have natural log of 4 there. We want to use we want the population to triple. It's going to be, instead of natural log of 4, it's going to be natural log of 3. We'll type that into our calculator. Natural log of 3 divided by 0.01 is 109.9-ish. Alright, we are almost done. 2 more problems. You open a savings account that pays 5.35% annual interest compounded continuously. After how many years will you have twice the amount you deposited? So usually we use A equals, well, they wrote it right above there. We we plug in for A and we plug in for P. The issue is they didn't give you a P value here. But remember, we did this in the day 10 video. Actually, maybe it was the beginning of this video. I don't know. They're all blending together for me. But if we want something to double, we're just going to put a 2 over here, and we're not going to bother about a p value. E to the RT power. 0.0535t. Because the first thing you would do before solving for t would be you divide whatever this number was to the other side, or you divide this by that number first, and we'd end up getting 2 if the amount we want is double the principal value. All right, to solve this, we natural log both sides to cancel out this e, and then get rid of the 0.0535 by dividing it on both sides. All right, type that into our calculator. I'm going pretty quick on this one. not going to be an overly long video. This is nice. Natural log of 2 divided by 0.0535. 12.9-ish. We'll call that 12.96. I think we're talking years. Yes. All right. If you deposit 15, oh, I thought we only had 2 more problems. I guess we have 3. Maybe it will be a long video. If you deposit $1,500 into a savings account that pays 7% annual interest, compounded monthly, how long would you have to wait to have $5,000 in your account? So we want $5,000 in the account. Our principal value is $1,500. 1 plus our rate is 7%, 0.07, over N stands for the number of times compounded per year. Compounded monthly means N is going to be 12. All right, and then we need to solve for T. First thing I want to do is get rid of the 15,000. I'm going to divide 5,000 by 1,500, not 15,000. That gives me 3.333 continues. And then I'm going to simplify this part too. 0.07 divided by 12 is going to be so this is going to simplify to 1.00583, and the 3 repeats. So that's what that decimal is going to be, to the power of 12t. All right, unfortunately here we don't have base e, so I can't just natural log both sides and cancel out. So instead, I'm just going to log both sides. I can either log or natural log, doesn't matter. Either way, nothing's going to cancel immediately. But the whole point of that, is that I can bring the exponent in front now that I have logs. So it's going to be 12t times log of 1.00583 with a repeating 3 decimal. All right, and then the final thing to solve for t is I need to get rid of the 12 and the log of 1.00583. So I divide both sides by 12 log 1.00583. 12 log 1.00583, and that will be our answer for t. So type that into the calculator, clear out all this other stuff. Log 3.3333333. The more 3's I put there, the more precise my answer is going to be. Divide that by 12. I'm just going to put enter, but you don't have to. Divide by log of 1.005833333. Remember, the more decimals I put on there, the more precise my answer is. And I got 17.25 years. All right. How much money should be invested? What the heck? I kept thinking my answers, we were almost done, and then we weren't. I'm sorry, guys. We have 2 more problems still. How much money should be invested at 5.46% interest compounded continuously to yield 900 after 2 years? So the nice thing is this keyword, continuous interest. I get to use PE to the RT formula, which is really nice. A equals PE to the RT. That's much easier to deal with. So how much should be invested? So we don't know what our principal value is. But we do know we want $900 after 2 years at 0.0546. Oops, I forgot the E. That should go in between P. There we go. So I'm just going to solve for this. This is P times E to that exponent. I'm now just going to figure out what this decimal is and then divide it on both sides, and that'll solve for p. So get to my calculator. E to the 0.0546 times 2 power, and then I'm going to do 900 divided by that so I can solve for p. So divided by a second answer. So I got 806 point, we'll call that 90 dollars is how much should be invested if you want to get up to 900 in 2 years. Now we're finally at the last problem. Suppose a colony of bacteria is growing exponentially. If 16 hours are required for the number of bacteria to grow from 4,000 to 5,000, find the doubling time. So like always, we're just going to plug in what we know and use that to help find what we don't know. So we know we are growing to 5,000. So the amount that we end up with is 5,000. We started with 4,000. E to the, they didn't tell us the rate, so we just put R, but the time they told us was 16 hours. So just make sure we remember our units are hours. All right, so I'm going to solve for what the rate is now. Sorry, that should be 4,000. So I'm going to divide both sides by 4,000. 5,000 divided by 4,000 should be 1.25 equals e to the 16r power. And then I natural log both sides to solve, or to cancel out the e. And then I divide both sides by 16, and that'll give me the r. So, natural log of 1.25 divided by 16. That gives us that the rate is 0.0, and I want to put this down really accurate. So 0.0139. I want to put a lot of decimals on so I get a pretty accurate rate. 46472. And that's going to be our R value. But R isn't what we wanted. We need to use that R value to find the doubling time. Remember, if we want to see how long it takes something to double, we just put a 2 here times E to the, now that I know the R, I can put that here, 0.013946472 times T, because we're trying to find the doubling time. I'm going to natural log both sides. That's going to cancel out the E. Then I divide by that ridiculous decimal, 0.013. I'm not going to write it out, but I will when I type it into the calculator. And that will give me an answer for T. So natural log of 2, divide that by 0.0139. Oh, I guess that's good. 0.013946472. You don't really need that long of a decimal, but the longer the decimal, the more precise. So 49.7 minutes. No, hours was our units. All right, so that was a little bit longer than most of the types of problems that you'll be dealing with. And I'm sorry I had to rush a little bit because my video went long again. But thank you guys for listening, and have a great day.